Thanks, Jimmy. Just to double check, everybody hearing me okay? Yes, good. Before I actually start the presentation, I want to just give you a little bit of history as to why this class was put together. I'm old. I used to not want to say that, but I can't change it. I'll be 80 years old next June, and my first year of teaching was 1971. I started in a high school auto shop, but before that, I was wrenching and spent some time in the Navy. I can remember when the Corvette split window in '63 was a brand new car, and my point is, back then, there was a weakness in technicians, in students, and in mechanics on understanding basic electricity and how to apply it to fix a vehicle. This is 2025, X number of years later. I've traveled extensively around the country, training primarily high school and college instructors in the various topics of technology. And I find that there is a weakness on the understanding and application of basic electricity throughout the industry. It's still there. And terms like voltage drop, Ohm's law, circuit loading, all of those things are becoming, to me, more important than ever before. And it's my passion to give you today some usable tools that you can take away with and use for your students tomorrow or next week or whenever. I really feel strongly about this subject. And now we have EVs coming at us from all directions. They're all electric. There are certainly procedures that must be followed. We could get into that later on, but if you're going to the Vision Conference in March, we're having a 4-hour class session on teaching electrical strategies, especially with EVs. So it's the top hot topic. It's out there. It's in demand. Each of us as an individual has to stand in front of a mirror and ask ourselves, are we comfortable with our current knowledge of electrical and our ability to share it with students? If we are, great. But I still think, hopefully, that's my passion, that today will give you something of value and you can come away with it feeling that, hey, my time wasn't wasted today. The old guy can still not drool too much and give me something of value. So that being said, I want to encourage you, just a little different webinar than what you might be used to. If you have a question or you see something on the screen that you don't quite understand and you want to ask a question, interrupt me immediately and ask me that question. Don't wait for a time. If you want to put it in the chat, that's fine. Somebody will monitor that, but I would prefer interaction at the time that you see it. So that being said, let me try to share my PowerPoint here and I'll give you some hopefully good news. Let's see. Slideshow. What is going on here? I got a little technical difficulty. Give me a moment. I'll recover. At least try to. Okay, now let's try it. Here we go. Okay. And hopefully, if I've done everything right, you should see a PowerPoint slide on your screen. Can somebody say yes or no?
Yes.
Oh, okay.
And Dick, do you want to mention the certification they get at the end?
Oh, yes. This class has been authorized by ASE that if you stay to the bitter end at 5 o'clock, we will give you a certificate indicating that you have 2 hours towards your 20 requirement. And that's something that we do with ASE. So if you have a trainer, I hope so, have it plugged in and set up, have at least one extra digital meter available, have your jumper wires ready. Today's class will work with either the 1905 or 06. And if you got a 12-volt test light, have that handy also. This is a judgment-free zone today. Nobody is judging you on what you know or what you don't know. I don't like to get into that. I'm old and I've got a lot of experience, but that doesn't make me any smarter than anybody else. In fact, I learn every day from you. So if you got something to share with me, I would love to have you do that. Please ask your question at the time that you are thinking of them, and please interrupt me. Note-taking will not be necessary. You will get a PDF version of this PowerPoint. Right now is 116 pages. Every slide, every text, every schematic, all assignments, and all of the answers will be included in that PDF. If you stay to the end, we will send you a copy of that via email. All step-by-step procedures and schematics will be included, clearly identified. This PDF version is designed for you to use as assignments for your students. And please contact me after this session if you have any additional questions or requests for help. And here's my contact information. You may want to take a screenshot or jot that down. There's my email and my cell phone. I don't mind giving that out. Call me anytime. I'm in Michigan, and I'd be happy to discuss with you anything you wish. I'll give you a minute just to jot that down and we'll move on. A deep dive into Ohm's law. Ohm's law is much more than just a formula. When I first started teaching Ohm's law in the 70s, I taught it the way I was taught, math. Series circuit, 1 R1 plus R2 plus R3, parallel circuit, 1 over R1 plus 1 over R2. My students would fill in all of the answers, would turn in the answer sheets, probably with all passing grades, and not one student would learn anything about fixing a car. Math does not work for teaching Ohm's law in 2025, in my opinion. Now, if you want to twist in voltage drop testing to teach Ohm's law, now you got something that will work. This class will cover basic electricity, voltage drop testing, procedure, diagnosis, and evaluations, understanding open circuit voltage testing, what it means, seeing and understanding electrical phenomena, what is a digital meter impedance and how do meters work, what is circuit load testing and why is it important. Many of you know Scanner Danner, Paul Danner is a good friend of mine. And you've maybe belonged to some of the Facebook technician groups and you always hear stories about, well, I ohmed it out. But the really problem that I found was found by load testing that wire or that circuit or that harness. We'll talk about that today. Practical applications of Ohm's law. We all know this formula, volts, amps, and ohms. And of course, there's a second formula that you can blend in watts. Now, we're not going to spend any time on this today, other than we'll talk about watts just a little bit. But there's a second Ohm's law simple formula that can be used to determine. If you know two, you can find the third. Got to have two known, and then you can find the third, whether it's watts, amps, ohms, or volts. Your students always ask, why do I have to learn this stuff? How does doing math problems help me diagnose and fix a car? How is this stupid triangle related to me going and fixing something on the car? And we can answer that question today. It's my opinion that an efficient and accurate diagnosis of an electrical circuit requires the following things. Number one, you need a circuit-specific schematic and a thorough understanding of how it works. If you don't have that, you're going to have a difficult time fixing electrical systems. You're going to probably resort back to the history of repair. The last car I saw that did this, I replaced this and it fixed. If you do that, you're going to be about 50 to 60% accurate. 40% of the time, you're going to make a wrong mistake. So you need an accurate schematic for the circuit you're working on. Secondly, you need a clear understanding of the relationships between ohms, volts, and amps, which is Ohm's law. Not having either will result in guesswork, perhaps component damage, and time wasting. A quick review. To find resistance, you divide volts by the current. You define current, you divide the volts by the resistance, and then to find voltage, you take the resistance times the current. That's something that should be in everybody's head. Not necessarily the math portion, but the relationship. Circuit behavior rules. If additional resistances are added to a circuit in parallel, the overall circuit resistance will drop, the current will increase, and the same voltage is available at each resistance branch. That's a parallel circuit. If additional resistances are added to a series circuit, the overall circuit resistance increases, the circuit current decreases, and the circuit voltage can be different at different places in the circuit. Most circuits in the vehicle are series with one path for current flow. But if unwanted resistances are added, it becomes a compound series circuit, which reduces voltage and current in that circuit. This is critical to understanding what's wrong with my car. Voltage drop testing and circuit loading are the best methods of determining unwanted resistance. And there's the most common cause of circuit problems in today's cars. Unwanted resistance is in the circuit. We don't either know it or we don't know where it is or how to find it. So the question becomes, how do I find the unwanted resistance in a circuit? Knowing the answer to this question and be able to accurately do it is the difference between diagnosing a problem with accuracy or pure guesswork, even if it's logical guess. A quick review of static and dynamic resistance. Now, this is the only assignment that we're going to talk about today that's in your existing, if you have an Ohm's Law trainer, that will be in the curriculum. Everything else that we do today will not be in the curriculum. So right now we have our trainer, and I want to stop just a second here and show you this. Bear with me. Okay. Can you all see my trainer now?
Yes.
Yes? Okay. This is a CL-1919-06. The 6 is the fluke meter. This L3 bulb is an LED. And some of these colors of the sockets have changed. The 05 were white, these are yellow. The 05 had the X-Tech meter. The 05 had the incandescent L3 bulb. The 05 had some of the bayonet connectors that were a little bit hard to work with, and now the 06 has the bananas. So if you have an 06 trainer and you want to increase the current flow of L3, the curriculum had to be rewritten because this on the 05 is the largest current taker of all of the parts on the trainer. This drew about over 3 amps. But because we got the trainer certified by CSA, they soon realized that, hey, this bulb gets hot enough to burn students. So you cannot have an incandescent bulb that'll burn a student. You got to put a shield over it or something. So we took this bulb out and we put in the LED 3157. They totally interchange. If you have the 05, you can put this in. If you have the 06, you can put this in. It makes no difference. The difference is the current flow now will be much, much less. This is one of the few current consumers of the trainer. It used to be the greatest. Now it's the least. So if you want to have a high current device, look at the 05 curriculum, put the incandescent bulb in there, and you got a whole new set of assignments. Okay, just want to touch base with that. All right, so let's go back to the PowerPoint. We're going to go slideshow from current. Okay. If you have the trainer in front of you and your meter, measure the static resistance of L1 bulb and calculate the estimated current draw of the bulb. So you take your ohm meter and you measure the resistance with the trainer off of L1. Now the students have done this in the assignment if you followed the curriculum. Now depending on your bulb, and it's going to be variation, you're going to get about 4 to 5 ohms, somewhere in that range, 4.8 ohms. Trainer is off, the bulb is off, you're just simply measuring the resistance of the bulb. So if we have a 14.5, and it could be 12, it could be 10, it could be anything you wanted, I'm going to use 14.5, which is a typical running voltage of a car. I'm going to calculate the current draw of that bulb by using Ohm's law. And I do that by dividing the voltage by the resistance, and that gives me an estimated current of 3.02 amps. So the answer to my question is the static resistance is 4.8 ohms. The calculated current draw of that bulb is 3.02 amps. Ohm's law doesn't lie. Now let's do the dynamic resistance of that bulb. So we have static resistance when the bulb is off. We have dynamic resistance when the bulb is on. How do we calculate dynamic resistance? Many students make this mistake. They try to use an ohm meter to measure dynamic resistance, and you cannot do that. Instead, you've got to measure the source voltage. We have 14.5. Again, it could be whatever you have. Now we set up our ammeter to read the current flow of L1 bulb. So here you see the meter is set up to read amps. You could put the meter in the ground side if you want. I've got mine in the positive side. And I'm going to record the amperage of the bulb, which is 273 milliamps or 0.273 amps. Now again, yours will be a little different, but it's going to be in that range. At that point, we use Ohm's law and we calculate L1 dynamic resistance. We do that by dividing the voltage by the current, and that gives us 53.11 ohms. Why is it different from static to dynamic? Anybody want to venture an answer?
Don't be shy. Come on.
Somebody volunteer. Why is it we have a huge difference between the two resistances?
As the bulb heats up, the resistance changes?
Exactly. If I had, in my live classes, I have a bag of Snicker bars, and I throw a Snicker bar to anyone to give me the right answer.
So well, I get Snicker bar.
You get a Snicker bar. Thank you. The bulb's resistance substantially increases when illuminated due to the heating of the filament. This is how an incandescent bulb works. We get light from the energy of the heat of that filament. Static testing of a bulb only confirms that the bulb has continuity. It is a worthless test. I've seen so many students and instructors test a bulb with an ohm meter. You're wasting your time. You got to check it dynamically. Okay. How many times have you heard someone say, I ohmed it out and everything's good? I'm a little suspicious when I hear that. Let's test this wire with an ohm meter. What's it going to read? It's going to read 0. Let's test this wire with an ohm meter. All of the strands have cut away except one. What would the ohm meter read?
0. Near 0.
0. this is why ohmmeter testing is not on my big list of favorite ways of diagnosing a circuit. Resistance testing has its place in circuit diagnosis, but can be easily confusing if you do not understand the difference between static and dynamic resistance. That's a huge problem for students. I want you to build this circuit if you have a trainer in front of you. If you don't, you can do it later. So here's a circuit I want you to build. I want you to bring a wire to the fuse, through the fuse to the switch, from the switch to R3, from R3 up to L1. And when you get that done, you build the ground circuit. So now we have this circuit built. I'm gonna get caught up here myself. Okay. And then let's get the grounds. Okay. If you're building that circuit, hopefully you've managed to get it done. I want you to adjust your voltage, if you can, as close as possible to 14.5. It doesn't have to be 14.5, it could be 12, but to get the numbers the same as mine, close to 14.5. The L1 bulb in this circuit could be any device in the car. It could be a blower motor, it could be a fuel pump, it could be a power motor seat, whatever. There is unwanted resistance in the positive circuit, which is R3, and also in the ground circuit, which is R4. In a vehicle, the actual location of the unwanted resistance would be unknown. Everybody okay with that so far? All right.
Perfect.
Okay, circuit understanding. This is the circuit you just constructed. What type of circuit is it? It could be parallel, series, or combination. So what's the answer?
Series.
Series circuit. Very good.
Can I have my bar?
Sure. I don't know how far you are from me, but I'll try to throw it. So we have R3 and we have R4 in series with L1. If we remove R3 and 4 from the circuit, it's still a series circuit, but with only one path for current to flow in a single desired resistance. Voltage drop testing. When should we voltage drop test a circuit? Anytime that you are not 100% sure of your initial diagnosis of the circuit, or to confirm that the new component you are about to buy and replace will indeed fix the problem. I'm fairly well connected with the industry. I have a lot of friends that are in business, and they tell me a typical AutoZone or O'Reilly's or Advanced, 40 to 70%, depending on the incident, of the electrical parts that are returned, there's nothing wrong with them, especially alternators, starters, and modules. That's huge. That's why a lot of policies are no return on electrical parts, no return on electrical parts, because they're guessing, they're diagnosing with guesswork. To check both the positive and ground sides of the circuit for unwanted resistance. These are the three main reasons we do voltage drop testing. You don't have to write this down. This will be available to you on your PDF, but here are some excellent resources for your students or you on voltage drop testing. These are articles on the web. If you go to YouTube and search these following categories: you will get some very, very good videos on helping your students understand voltage drop testing. Huge resource here. Okay, voltage drop testing. It is the measuring the difference between voltage of, if any, between two selected points in the circuit. In other words, if you put your voltmeter here and the other lead of your voltmeter there, if you get a voltage reading, it's telling you there is resistance between the two places you just touched with your voltmeter. That is an important thing to remember. Acceptable voltage drop should be close to zero. Switches can have a few tenths. Connectors and plugs should also have almost no voltage drop. Maximum allowable voltage drop charts are available. That gives you acceptable voltage drop values change based on the current. GM has switched recently. Instead of saying a maximum of 0.6 of a volt, they're giving percentages now, 4 to 5%. The total circuit current, 4 to 5% voltage drop. The amount of voltage drop will increase or decrease at the same resistance based on the amount of current flowing in the circuit. What does that mean? Well, if you had let's say a 0.3 of a volt drop between those 2 points and the circuit had 1 amp in it, if it flowed 10 amps, that voltage drop would go up. Voltage drop testing should be learned and mastered by any student or technician working on vehicles today. Guys, I've traveled all over the country. I've trained thousands of people, and I can tell you there's a weakness in understanding the true value of voltage drop testing. Another great resource, if you haven't found out yet, go to gmupfitter.com. Free resource. I love free. Free is one of the few good 4-letter words I use. So if you go to that website, you click on Best Practice Manuals. You'll get this. Click on Electrical, and you're going to get a whole bunch of good information from that resource. It's a dynamic document. I can't talk about it enough. Now you've heard about
FYI, everybody's going to get a copy of this PDF.
Yeah, you're going to get all of these links, no problem. Now, if you want to complete GM set class, many of you don't know this. If you don't belong to IATN, you should. So you go to iatn.net, join free basic membership. Now you can join with a corporate membership, gives you more resources, but no, just go to IATN and join free. Then here's the home page. After you log in, this is what you see. You're going to click on resources. Then you're going to see this page, OEM training information. Look at the stuff that's available there. GM, Ford, Chrysler, Toyota. Click on GM, and there is your entire set class, all 3 parts of it. There's the index for the first part. Covers all about electricity, all about components, all about voltage drop testing, current testing, how meters work, the whole 9 yards. Again, it's free. Your students can access it the same way. You can download it, whatever you want to do. This is a powerful resource. And every time you guys go to a conference and you network with people, you come back with something, hey, I wish I'd have known that sooner. This is good stuff, guys. Okay. Here is my representation of a circuit with no unwanted resistance in it. We have a simple battery, a bulb, and a multi-wire connector. We put a voltmeter on the bulb and we get 12.09 volts. We started out with 12.6. We call that the loaded voltage. That bulb is going to draw some pressure from the battery, so it's not going to be 12.6. It's going to be high, but 12.09. This variation will depend, of course, with the power source. The circuit current is 236 milliamps. Bulb resistance calculated dynamically is 51 ohms. The bulb is bright. There's no problem here. This is the normal reading. Now let's put some problems in the circuit. Here's a circuit with unwanted resistance. Now we see that the current has dropped to 194 milliamps. The source voltage at the bulb is 8.19 volts. What does that tell us? It tells us that something else in that circuit has stolen some voltage from that bulb. The loaded voltage at the bulb is 8.19 volts. The circuit current is 194 milliamps, but if we check each side of the multi-wire connector, we get 3.91 volts. That is a voltage drop test. It should be 0. It's not. It's 3.91. That means that we've lost almost 4 volts, taken it away from the bulb. Bulb resistance now changes. That's why dynamic is so important to understand. The bulb resistance changed to 45 ohms, using Ohm's law to calculate it. And now the circuit resistance is 65 ohms, which means there's 20 ohm resistance right there at that connector. Now we would have never seen that if we didn't check a voltage drop with the meter. That's why the bulb is dim. Remember this important statement. If there is not full source voltage available at the device load while it's turned on, there is unwanted resistance somewhere in either the positive or ground side of that circuit, feeding the load. Point-to-point testing, checking for voltage drop, is the best method of locating the unwanted resistance. Let's do some hands-on stuff if you have the trainer in front of you. There are many different methods of voltage drop testing. Now, you may have your preference, and that's fine. I have mine. Some other person may have theirs. No one system is best. It's based on the preference of you, the technician. So let's go back to our circuit. Now we'll switch our meter over to volts. The source voltage in my case is 14.6. Yours could be different. We're going to measure V1. V1 measures the voltage at the bulb between A and B. If you want to do that, go ahead and do that. This is the circuit we built earlier. The source voltage is going to be around 7.21 volts. Conclusion from that reading. What does that reading tell us? Tells us that the bulb has less than source voltage, which means there's resistance somewhere else in the circuit. Now let's do V2. V2 measures terminal A, positive of the bulb, down to the plus battery. We got 3.708 volts. And by the way, there's the circuit we just checked. The dotted lines represent that entire circuit. And the conclusion is we have resistance somewhere in the positive side of the circuit. We don't know where it is yet, but we know there's resistance there. Now let's do V3. V3 checks the ground circuit. We go from battery ground to the ground of the bulb. And we get 3.685 volts. Conclusion, there's the dotted lines represent the path that we just checked the voltage drop of. And the conclusion is we got unwanted resistance in the ground side of the circuit too. Total voltage drop, you add those three together, you get 14.6. But the bulb's only running on 7.21. Conclusion from these readings, there is unwanted resistance in both the positive and ground sides of the circuit, but we don't know where it is yet. To find the location of the unwanted resistance in the positive side of the circuit, let's do this. V1. V1 checks positive battery, wires to the fuse, through the fuse, wires to the switch, ready to go somewhere. So we're checking V1, and the readings on this is 0.010 volt, 10 millivolts. Not much at all. Conclusion, nothing wrong here. That's normal. So the X's represent where we just checked. We've checked from the battery source to the switch. There's no unwanted resistance there. So let's check V2. V2 is going to check the condition of the switch itself. And we get 0.009 volts, which is perfect. Nothing wrong with it. And we've checked those two X's. That means we've checked the mechanical function of the switch. Let's check V3. Those are two accessible points in the car. And by the way, I've seen technicians start ripping into harnesses and laying on their back under the dash, ripping things apart when they have no idea where the resistance is. Voltage drop testing at accessible points will give you a clue before surgery where you need to be looking for your resistance. So the source, or the V3 voltage, is 3.660 volts. Aha! Conclusion, you've just found your unwanted resistance between those two X's. Let's do V4. V4 is 0.001 volts, which means there's no unwanted resistance there. So you have found the exact location of your unwanted resistance is between the two blue arrows. If that's the end of a harness, then you need to open up the harness. Any questions? Again, this is only one of many ways of checking voltage drop. Let's find the resistance in the ground circuit. V1, we check the ground of the bulb to test point P, and we get 10 millivolts. Nothing wrong. Conclusion, no unwanted resistance. And we've checked between those two black X's. Now let's do V2. Well, we can predict what the reading is going to be, 3.676 volts. There's our unwanted resistance. We check those two X's. Now V3, we check from battery ground to the ground of our last test point. This is all ground circuits now. And we get very, very little voltage drop, which means it's good. We've checked between those 2 points, and we found our unwanted resistance between those two blue arrows. Hope this makes sense. This is an easy way of doing voltage drop testing. Now we're doing it on the trainer, but this same application can be used on a vehicle. In fact, it must be used on a vehicle.
Quick question.
Yes.
So both sides of the circuit had equal voltage drop. So does that mean resistor 3 and 4 are the same resistance, same amount of resistance?
Excellent thought. You are correct. Both of those resistors are 20 ohms.
Okay, perfect.
You're right on the money. You get a virtual Snicker bar. Okay. There are many different methods of measuring voltage drops. The differences are where the two ends of the voltmeter are connected to the circuit. The differences are preferential and, if fully understood, do not change the accuracy of the tests. If a voltage drop is detected, some guys choose to temporarily bypass what they just checked with a jumper wire to confirm they found one. Now, I sometimes do that and sometimes I don't. But it's a like, okay, have I really found it here? Let's bypass it. Oh yeah, it's cool. So that's one thing you can do. Now, you're not going to have time to do these because I'm going to show you all the different ways of doing voltage drop testing. And the reason I'm doing that is because you can have this available to you after the class, and you can run your students through these different methods. So what have we done here? We've got the same circuit built with the two resistors, but now we have the voltmeter with the red probe fixed to the positive battery post, and we have a movable black probe. The first test point is test point 1. We're at the battery side of the fuse. It has 0.004 volts. Test point 2, we've checked the fuse. By the way, if that fuse was blown, we would get 0. So we know the fuse is good. Next, we do test point 3. We know that wire is good. We do test point 4 with the switch on. We know the switch is good. We go test point 5. We still got low voltage. We know that the wire is good. We go test point 6. It jumps up to 3.529 volts. Aha! There's our problem. Now we go up to test point 7. We get the same similar voltage drop. Why didn't it go to 0? It didn't go to 0 because our meter is fixed on the positive side. So the resistance at test point 7 is going to affect the test point 6 is going to affect the same at test point 7. So you're going to get two very similar voltages there. Now, if you had the separate meter leads to go from 5 to 6 to 6 to 7, then it would be different. But here, because you've anchored one lead of your voltmeter and you're moving only one, you're going to get that reading. Any questions? So let's reverse things. Let's make the black lead of the meter permanent to ground and move the red probe. Test point 1, 14.5. Test point 2, 14.5. Test point 3. Test point 4. Test point 5. Look what happens at test point 6. We dropped the inverse. Before we were checking to positive, or I mean to ground. Now we're checking the difference between 10.91 and the other 3.5 something is source voltage. So it doesn't matter as long as you understand where you're checking. There's your problem between 5 and 6. Test point 7 will be the similar one. It's the same test, it's just the inverse voltage. Here's another option. With the red lead to power, the black lead movable. Now we're checking the ground side. Test point 1, test point 2, test point 3. It changed. There's your problem. Either way, we'll find that problem. So now we have the red lead movable, the black lead fixed, and we're checking the ground circuit. So there's 1, 2, 3. Aha, there's your problem. So these will be available to you just as they are. Now here's another way. Here we have the circuit, and we have one lead of the meter grounded to the negative battery terminal, and we're going to test all of the circuit at one time instead of doing positive and ground separate. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Question: which red probe readings will show a voltage drop?
Six and 10.
Anything after 6?
6, 8, and 10.
7, 8, and 9. 6, 7, 8, and 9. Now there's a little discrepancy there, and that's fine. I'm just trying to tell you this is what we need to reinforce our understanding of what voltage drop effects are in a circuit. Now you can do this circuit at yourself, and you'll prove that those answers are correct. Here's another option. This is my preference, and again, you don't have to do it because I do it, but this is the way I like the voltage drop test. Here we're going to have a meter, and we're going to move both leads instead of one. So I'm first checking the battery, make sure I got good battery voltage. Then I'm going to check here. That's a wire. I'm going to check there. That's the fuse. There, that's the wire. There, that's the switch. There, that's a wire. There, that's another connection point. There, 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 and there. Which meter readings will show a voltage drop?
Seven and 9.
7, 9,
11.
and 11.
Yep.
Now this is a good exercise for your students, guys, and this is all going to be available to you. So I hope you're going to come away with something useful. Any questions on voltage drop testing before we move to circuit load testing? Okay.
Hey, Dick,
Yeah.
I have a question. It's Joe Hart.
Sure. Yeah,
On that last one, can you go back to that last slide for a minute?
absolutely.
And I've ran into this where students don't understand this. 5 has to be closed for that not to be a.
Oh, absolutely.
drop as well.
And
So
you're
5's going to
correct.
be 5's going to show you a drop as well.
A little bit, yes. I'm talking about significant
Right,
drops.
right. No, but
you're right.
if it's open, it's gonna show.
That schematic should show a closed switch. Otherwise, we wouldn't get anything on the down leg side. You know what? I'm going to fix that. That's
So-
correct.
Well, so when I draw this on the board, I like to cross it. So
Yes.
and then I check them with it both ways. Hey, you've got to know this. And
Well,
then
not
stimulate
only
a
that,
bad switch.
but if you check voltage drop across an open switch, you're also checking the whole circuit beyond that switch if you get both source voltage. If you don't, you got an open in that wire somewhere.
Well, that's a great point. That's
Thank
a
you.
very good point.
Thank you.
Thank
I
you.
try to get one. I could try to get one a day.
Thank you.
Okay. Circuit
Good to hear
load
from you.
testing. Thank you.
Good
sir.
to hear from you, by the way.
Oh, you betcha. I hope we go cross paths here soon. This is a much more accurate way of testing a circuit for problems. Paul Danner is just a fastidious guy about circuit loading. And Paul and I work real well together. So here's loading a circuit with a calculated amount of current to determine if any resistance is present. Typical application of circuit loading. We're going to test a harness, whether it's laying on the bench or we got a fuel pump circuit from under the hood back to the gas tank. Is the harness got corrosion? Is it got rust, dirty, whatever? So here's the harness. Whether it's in the car or out of the car, we don't care. And we're going to pick one wire of that harness to test. So there's one end of the wire, there's the other end of the wire, and we're going to hook up our ohm meter. What have we just done? We've wasted our time. An ohm meter is not a good test of a wire. We've got to load that wire to see if it will carry the current without a voltage drop. So let's get rid of the meter and let's test this wire the right way. We're going to come up with a battery and we're going to ground one end of that wire to the battery. We're going to come out of the battery with a fuse. We're going to go through an ammeter. We're going to come out of the ammeter and go to the load. In this case, I'm using a 194 bulb to load that wire. I know what the amperage draw of the bulb is. It's 287 milliamps. And so if I have a reading close, could somebody mute your mic there with that background noise? Thank you. If we have a current draw close to the source voltage and current of that bulb is 287 milliamps, I know that wire does not have any resistance in it that would steal current from the bulb. However, if the ammeter read 100 milliamps, I know that something is taking current away from that bulb, which is the load, and it's got to be in that wire somewhere. And I could use voltage drop testing to figure out exactly where that unwanted resistance is. This is circuit loading. Now I've only used a very small draw bulb for this particular circuit. So we can do this on our trainer. We can hook up our circuit now and just tear apart the circuit you had, and we're just going to simply put the L1 bulb in series with the ammeter, and we're going to put it on the positive side of the circuit, and the ground goes directly from the bulb to ground. And we're going to read the normal current of that bulb. So the ammeter is properly shown here to measure the current flow in this circuit. It's not the current flow of the bulb, it's the current flow of the circuit. So we got 287 amps or 280.287 amps or 287 milliamps. Now we're going to change by adding another black wire. We're going to run the wire that used to go from ground over to terminal P of R4, and we're going to come out of P and go to battery ground. The current stayed the same, which tells us those two wires are good. But if we change one of those wires from P down to Q, notice what happened to the current. It dropped, which tells us there is now resistance in the last point you tested. So now we're using the current draw of the bulb to load that ground circuit. And we found there's a resistance. If we change both of those wires over to R2, it went down to 182 milliamps. The bulb is much dimmer than it was because that R2 resistor has got to be more resistance than R3. R3 is 20 ohms, R2 is 40 ohms, so we've doubled the resistance. And then if we move it to R1, the bulb is barely on, it's only drawing 112 milliamps. It's supposed to draw 287. So that R1 must be a very much higher resistor, and it is. It's a 100 ohm resistor. But we're using current load to find unwanted resistance. The circuit was loaded with a bulb of 287 milliamps. The rule of circuit loading is you must load the circuit with the same current that it normally uses in the vehicle. So if we wanted to test a fuel pump circuit, we would not use a 287 milliamp bulb. So we would look at the fuse of the circuit and say, okay, it's a 10 amp fuse. So we want to load that circuit with 10 amps. Never exceed the current capacity of the circuit wires or components. Many use multiple incandescent bulbs able to be switched to add more bulbs in parallel. Many different types of circuit load testers are available for purchase. Now let's check that fuel pump circuit. So here's a typical fuel pump circuit. Comes out of the battery to a fuse, goes to a relay, goes to a multi-wire connector, another multi-wire connector, finally down to the fuel pump connector, and the fuel pump comes out of the fuel pump, goes to ground, goes to a multi-wire connector, another multi-wire connector, finally to ground somewhere at the chassis. So there's a typical vehicle fuel pump circuit. This is not the control side now. This is the high amp side. So let's load test this circuit. First thing we do is we pull the relay out and we jump 30 and 87 with a fused jumper wire. We unplug the fuel pump connector and we ground the positive wire of the connector. We find a good ground back there somewhere and we jump the positive wire of the connector to ground. Then we go from the battery to our load fuse, through our 10 amp load, through an ammeter, and then to the fuse of the fuel pump circuit. And we have loaded the positive side of that circuit with 10 amps. And we're reading the ammeter to see how much amp is flowing through that circuit. If it's low, we know we got voltage drop somewhere.
What
So
what could we use? Sorry, what could we use for the 10 amp load again?
Let me show you that. Let me answer your question in just a couple of minutes.
Perfect.
So there's how to check the positive side. Here's how to check the ground side. Now we unplug the connector and we jump, make sure we got a good ground wherever it's grounded. And then we take the load tester and we put it to the ground side of that connector at the pump. Now we put that same 10 amps through the ground side of that circuit. Now we're checking the ground circuit with a 10 amp draw. If it reads 3 amps on the ammeter, we know we got some high resistance in that ground circuit somewhere. That's how to do the ground and the positive. We do those separately. You can't do it at the same time. At least I don't like to, because I don't know where the problem is. All right, to answer the previous question, what do you use for a 10 amp load? Circuit load testers are available to buy, or you can make your own. I made my own. One example is called Loaded from Joe Cashy at jogsautoelectric.net. I'm not involved with him. I'm not selling his product. It's just one source that he put together those incandescent bulbs in a box with switches that you can control in parallel how much load you put on a circuit. I'm building my own. You'll have this schematic in your handout. So there's the circuit I designed. And you have 5 switches here that you can add 5 bulbs, and you can choose which ones you want, 194, 3156, 9004s. They all draw different amounts of current. And you simply flip switches to increase the load. Now you got to have an ammeter in series somewhere so you know how much load you're putting on that circuit. Has anybody made their own load tester? They're quite easy to do. You can load test the ground side separately or the positive side separately. This circuit loading is extremely important, especially in engine performance and 5-volt reference sensors and signals. Man, is that common that they cause all kinds of problems. You throw sensors at it, it still doesn't fix the problem. And you checked open circuit voltage and you said everything's fine. No, you don't do that. Here we'll talk about open circuit voltage testing. Any questions on circuit loading before we move on? Open circuit voltage testing. What is it? What it isn't? Can it be useful? How to use it for diagnostic purposes. So let's go back to our circuit. Build our original circuit with the 2 resistors, R3 and R4, with the L1 bulb, just like we did originally. Have that circuit built up for you. And now I'm going to connect my voltmeter to L1. And if the connector of the red and black wires are plugged into L1, and my voltmeter is on it and the trainer's on, am I going to get source voltage? No, I'm going to get less than source voltage because of those 2 resistances in the positive and ground side. And I think it might be good just to prove that to you. So I will do that. Okay, let me stop this and just share my screen here for a second. Okay. Okay, so what I've done is that same circuit. My voltmeter is reading 7.19 volts at the bulb. Guys and gals, if we have them, this is a very big problem with technicians, students, and some even instructors. If I have a problem with a car that comes in, let's say a dim headlight, we can all see that. I've seen students almost every time bring the car in, look at the dim headlight, say, okay, left side's dim. They open up the hood, they unplug the headlight connector and check a voltmeter in that connector. Watch what happens when I do that. Watch the voltage. I'm going to unplug the connector to the bulb. The voltmeter went from 7.23 to almost the same as source voltage. That is open circuit voltage. Is there resistance in that circuit?
None.
Oh, I disagree. Aren't these two in the circuit? Aren't they still there?
Yes, they are, but
Yeah,
Yes, they are.
But they're not completing the loop. You're not completing
it's
the
not a
series
complete
circuit.
circuit. You're just checking powers and grounds.
So you say there's not a complete circuit there. So why does a voltmeter read something? If there's not a complete circuit, how could it flow through those resistors?
It's not loaded, so it's open circuit voltage.
Well, I appreciate your comments. Let's go further. Okay. Measure the open circuit voltage, 14.5. Why? It seems with the load removed, it seems to be an open circuit. But when the voltmeter is connected where L1 was, the circuit connected through the voltmeter, this is open circuit voltage. So why did the voltmeter read full source voltage when the bulb was disconnected, but R3 and R4 were still in the circuit? Good question, Krieger. Let's give you the answer. How digital multimeters work. A meter's impedance. Have you heard that word before? I think you have. Can you ask a student what that, can you tell a student what that means? Hey, mister, what does this impedance thing mean? I got an experiment, by the way. If you want me to tell you about it, I will. You can use your students to demonstrate meter impedance. It's a phenomenal experiment. It really is fun. Impedance is the amount of internal resistance built into a meter. The purpose of impedance is to cause a very, very low current draw from the circuit being tested for voltage. Digital meters usually have very high impedance, while analog meters can have lower impedance. If you check DC voltages with a low impedance analog meter, you can get very inaccurate readings based on the circuit current draw of the meter from the circuit being tested. Now, what is an analog meter? It's a meter with a needle. Some OEM service information manuals warn against analog needle type meters when diagnosing and testing computer or module circuits on modern cars. You'll fry a module. Doing so can result in damaging or total destruction of modules, computers, and interfaces. Why? Because the meter draws too much current. So don't do it. How a voltmeter works. A voltmeter connects the meter leads between 2 points in a live circuit. Then it measures a very small amount of current flow in the meter, which is parallel with the circuit being tested. And using Ohm's law, it calculates the voltage. So there's something in a voltmeter called a shunt. And they measure the voltage drop between those 2 points of the shunt. The voltmeter's internal resistance is called impedance, and most digital meters have between 10 million and 20 million ohms. Now you know why I asked you to bring an extra meter. Put your voltmeter on the trainer on volt DC. Your separate meter, put on ohms and connect the common and volt ohm leads together. The meter that is away from the trainer will show you the resistance reading of the voltmeter output. In other words, that's the impedance of your voltmeter. In this case, it's 11.0 m-ohm or megohm. Now, depending on the brand of meter, it might be 20, it might be 13, but chances are it's going to be above 10 million.
Interesting. Minus 10. Yep.
Now, if you want to check opposite meters, you should switch one to volts and the other to ohms, and you'll read the impedance of the other meter. Now, why did that read open circuit voltage? Here's why. Using Ohm's law, we can calculate how much current this meter drawed from the circuit. For example, if we measure a 4-volt reading, it would draw 0.000000363 amps. 4 divided by 11 million, which is Ohm's law, gives us 3.63636364 e to the 7th power of 10. Now, guys, that is not a lot of current. The total resistance of the unplugged circuit with R3 and 4 in series was 40 ohms. Compared to the 11 million ohms of the meter, it totally ignored the 40 ohms, and the meter shows full source voltage as though there were no resistance present. That has to make sense. Questions? How an ammeter works. Direct ammeters are connected in series into a live circuit being tested, and the circuit current also flows through the meter. Most DC meters have a protection fuse to limit the amount of maximum current that the meter can measure without damage. Ammeters use either a shunt or a sensor built into the meter to accurately measure the amount of current flowing in the meter. A shunt is a calculated resistor used for measuring the voltage drop across it, and a sensor is usually a Hall effect type device that measures the magnetic field around the strength of the wire. Ammeters can be either direct reading or inductive. Direct ammeters must be inserted into a live circuit. Inductive ammeters are not directly connected into the measured circuit, but instead are clamped over the circuit wire and measure the strength of the magnetic field around the wire. There's the shunt that's built inside the meter. The current flows through those red wires, and the two little connectors there are where the meter reads the voltage drop. This is a Hall effect sensor that measures the field around the wire being measured. So here we have an ammeter direct reading hooked on the positive side of the circuit. Now, as you know, with a digital meter, if you reverse the red and black wires, it would still read amps, but it would have a minus in front of it. I just prefer to have it wired so it doesn't do that. So here we're reading amps on the positive side of the circuit. Here we're reading amps on the negative side of the circuit. Now notice that the red went on the ground side of the wire because current flow is still out of that bulb through the ammeter back to ground. So that meter would not have a negative in front of the reading. Now this is my inductive ammeter, and I have this one for a reason. I do all my parasitic draw testing with this meter because it's big enough to fit around a battery cable, and it's accurate to 5 milliamps. So all we're doing here, and those sockets have nothing to do with the meter. That has a combination volt-ohm ammeter. I use the ammeter function only. And there's the sensor that goes around the cable. Many of today's vehicles use inductive ammeter measuring devices around the battery cables to give charging information to the vehicle's computers that can vary the output of the alternator for energy savings. This all has to do with CAFE and EPA credits. How an ohm meter works. An ohm meter supplies a very small current across the unknown resistance and calculates the voltage drop across that resistance, and using Ohm's law, converts that to an ohm reading. Therefore, all ohm meters outputs a very small voltage to measure the voltage drop. It outputs a small voltage to measure the voltage drop. So let's hook your separate meter, put the ohm meter on the trainer to ohms, put the extra meter on volts, and you will read the output voltage of your ohm meter. Most of them are around ½ volt. It could be a little different. That is the output voltage that is used to calculate the voltage drop across the resistance that you've touched your 2 ohm meter leads to. Now, we all know that some meters have diode test functions. So while the meter is still connected like this, switch your meter on the trainer to diode test by pushing that yellow button until you see diode symbols there, and look what happened to the voltage. In diode test, the output voltage of the ohm meter goes up, and it has to go up because it has to forward bias the diode before it can test it. So if you've been testing diodes with an ohm meter, you've been doing it wrong for a long time. That diode was probably never biased. You've got to make sure that the voltage is high enough to turn that diode on. That's why diode test has a higher voltage than ohm meter test.
So to essentially close it, you mean?
Cause the diode to conduct. It's called forward biasing, yes. Any questions? Has anybody learned anything about meters today?
Plenty.
I hope so.
They aren't paying attention if they haven't.
That's why a circuit must be electrically dead when you're using an ohm meter, because you're putting out a voltage. How about using 12-volt test lights for circuit testing? There's people today that say test lights should not be used anymore. They are so wrong. You must know how much current your test light draws before you use it for testing. How do you do that? Well, here I've connected my test light, an old timer. Notice what I've done. I've come out of the battery side of the trainer to my ammeter, milliamps, came out of the ammeter to the probe of the test light, and grounded the test light to ground of the battery. And that test light draws, with a bulb on, that draws 201.4 milliamps. That's how you test the current draw of your test light. A test light can identify a source of ground or power depending on how the test light is connected. In other words, if you ground the test light, you're looking for positive. If you put the negative side of your test light to positive, you're looking for grounds. Here's a common test light. This one I bought at Harbor Freight for $4. I cut the alligator clip off of it, and I ordered some 4mm male banana plugs, and I replaced the alligator clip with a 4mm male banana plug. Guess what? I can use that test light now on this trainer. Many of you like to use test lights on the lighting trainers and the Ohm's Law trainers. That's how you do it. This test light draws 237.9 milliamps. Now, the reason I'm using my Fluke 88 here is just more decimal points. It's more accurate. But that's a $500 meter too, so we got 237.9 milliamps. Now here is a computer safe test light. This one is Snap-on. I bought it years ago and I think I've used it twice. Ridiculous waste of money. This is the one where it powers up with ground and positive, and if you touch a positive source in the circuit, the red LED will come on. If you touch a ground source in the circuit, a green LED will come on. But look what it draws, 11.56 milliamps. You say, well, that's good. It won't hurt anything. Well, that's true. It won't hurt anything. But when you get to use a test light better, you'll know you can energize fuel injectors. You can turn on ignition coils. You can cause relays to come on and off just by using a test light. But you need a test light between 200 and 300 milliamps to do that. 300 milliamps or less will not, guaranteed not, hurt any module or computer. More than that, yes. But you cannot energize anything with a test light that only draws 11.5 milliamps. Go to Scanner Danner's YouTube channel and just search test light testing. You're going to get really good education. Any
Dick,
test light?
Hey, Dick,
Go ahead.
I got a quick question, if you don't mind.
No, and I don't mind at all.
When we're talking about ohm meters or what have you,
Yep.
A lot of instructors teach it that the fact is you're really putting it in series because it's a power supply. I don't like to teach it that way because it confuses students when they're throwing the, when we have to set it up in series to measure amperage.
Well,
I don't know, what's your thoughts on that?
If you make that statement that you hook an ohm meter in series, you're wrong. You're hooking an ohm meter in parallel.
Absolutely. But a lot of instructors,
Well,
you know what I'm saying?
I
think
do.
erroneously. I think it's erroneous, but they explain it because the ohm meter is actually the power source. So technically it's in series, and I beg to differ.
No, it's not. It's in parallel, and they measure the voltage drop across the resistance that they touch the ohm meter leads to.
Well, thanks for agreeing with me.
Well, I agree with the truth, put it that way.
Yeah.
So any test light that draws less than 300 milliamps will not harm a computer. Test lights with these specifications can be used to energize electrical sensors. You can substitute a map sensor with a test light. You can substitute sensor signals. You can energize relay coils, fuel injectors, and ignition coils. Any computer-safe test light is not able to do this. Must be between 200 and 300 milliamps. Search YouTube Scanner Danner for test light, and oh man, you should just do that. Other methods of circuit load testing. Another method. Here we have our open circuit voltage testing at 14.5 volts. Now we're going to put a test light across the two ends of the connector. It's still disconnected from the load, and we're going to put a test light across the two ends of the circuit. If the voltage on the meter still is close to what it was source voltage, open circuit voltage, then there's no significant resistance in the circuit. If, however, it's 9.54 volts, 4.5 volts, if the voltage is less with the test light across the circuit, then you're telling you've got unwanted resistance in the circuit. You don't know where it is yet, but that's a quick test to see if you got unwanted resistance in a circuit. So open circuit voltage that used to be thought of as worthless and not valuable can be valuable. It also tells you that there's continuity of both the ground and the positive side. It doesn't tell you necessarily if there's less voltage in there, you got resistance in that circuit, but at least it isn't an open. If it was an open, the voltmeter would read 0. If there is unwanted resistance in a circuit, you can move the ground or the probe of the test light to determine the exact location of the resistance. So now you're using your test light as a movable probe, watching the voltmeter, and when it goes back up to 14.5, you found the resistance. So I have wrote this down for you, and this will be in your handout. So if you have resistances in both the positive and ground side, then you move your test light plug across the plug at 7.8 volts. Resistance in the ground removed is 10.53. Resistance in the positive removed is 10.53. Both resistances removed and so on. It tells you then if the resistance is in the positive side only, where to put your test light. If it's on the ground side, where to put your test light. For voltage drop testing with a test light. Here's another method. This is called the Load Pro. Let me show that to you. You need to be assured that I am not selling anything. This is just another option for you if you are interested. So here's our trainer. The same thing with unplugged. My open circuit voltage is fooling me. Now here's the Load Pro. All this is a kind of a test light device that I've adapted the two probes into 4mm male bananas. They're just like regular meter probes. So it's got the following leads on it. It's got a red to black lead with bananas that goes into your voltmeter. And then it's got a movable ground probe. So here's what you got. So you take a voltmeter and you plug the leads into the voltmeter. Set it to volts. And now I'm going to connect it to my open circuit connector. And I get my 14.5 volts. Now there's a button on the side of this handle. If I push that button, notice the voltage went down to 5.5. What I've done in this internal device is put a 50 milliamp load on that circuit. If it stayed at 14.5, I know there's no resistance in the circuit. But because there is a voltage drop, now I can use my probe to go to different points, push the button. Aha! I've seen the difference. So I can use this as a movable probe, just like the test light, just like the voltmeter, to find, without having to put any load on it, because the load comes from inside the tester. Again, it's the Load Pro. I'm not suggesting you buy it. It's just another option for you to load test a circuit. Okay, let's go back to our PowerPoint. Okay. If you're interested in this thing, simply Google Load Pro tester, and you'll get some videos, you'll get some handouts, places to buy them, Amazon, AES Wave, wherever you want. If you disconnect any component connector for diagnosis, there are only 3 possibilities for circuit problems. Think about this now. You've unplugged the connector to the blower motor or the headlight or whatever. If you have open circuit, either the positive or ground is open, no voltage will be present. That's telling you, hey, you got an open somewhere. Or you have a shorted circuit. If it's a positive short, or the ground is shorted to positive, it'll blow a fuse. If it's a ground short, you may not even know it unless the circuit is ground switched. Or if full system voltage is showing, that means you have continuity in those 2 wires, but you still may have unwanted resistance. And you'd have to go to voltage drop testing to find it. Here's another method of measuring current flow. This is going to be neat for some of you people that haven't heard this before. Voltage drop testing across fuses to determine the amount of current flow. Say what? So here's our circuit. Now we're all plugged back in. No resistance in the circuit. We just got L1 in series with the ammeter. It reads 0.264 amps or 264 milliamps. Now we're going to take our meter and measure the voltage drop across the fuse. And this meter, which is not as accurate as I'd like on low millivolts, says 0.008, which is 8 millivolts. I want to get a different meter with more decimal points. So I'm going to go to the old X-Tech meter, and it says 8.2 millivolts. Beautiful. Now I go to a fuse chart, and I'll show you where to get these. And this is for an ATO fuse, right there you see. There's the column of millivolt drop, which was 8.2. I have a 3 amp fuse, and it says if I have 8.2 millivolts, I'm drawing 264 milliamps. And that's exactly what my ammeter showed me. So this is a very accurate test, guys. It's a very accurate test. Now, here is sources that I have directed you to go to find out about voltage drop testing and where to get those fuse charts. They're free. You can get them for maxi fuses, mini fuses, all kinds of different ones. In order to do this test, you need very accurate, clean meter leads that are sharp. You can buy needle adapters for your meter leads, or you can get the probe adapters, either one. And the fuse terminals must not be corroded. This test is often performed after you've done a parasitic draw test, and you know you have excessive current draw out of the battery, but you don't know what circuit is causing the problem. So if you start doing the voltage drop tests across each fuse in the fuse box, if you get 0 voltage, there's no current flowing in it. That's not your problem. But if you have one that has current flowing in it, then you know you've had the circuit. Now you got to do figure out where that current is going. This is a very accurate and very valuable test. Any questions before we move on? Anybody use this test regularly? Yes, no? Maybe not, but you should. All right.
I'd like to see it again if we could go back for a second just to watch it.
Sure, no problem, no problem. We can do that. Let me just stop here and go back to the beginning.
Is the fuse installed while you do this test, or is the fuse removed?
The fuse has to be installed. You go to the fuse box. You don't touch anything. You leave everything the way it was, and you simply measure the voltage drop across the fuse. Now here I use the connectors because it's easy to get to, but you would actually touch those 2 test points. You notice every fuse has those 2 little test points right there and right there. That's where you'd put your probes on a car. Right there. Can you see my cursor? Somebody say yes.
Yes.
Okay. And here I got 8.2 millivolts. Now the circuit has to be on. And obviously it's on, or there wouldn't be a voltage drop. And you think, wait a minute, there shouldn't be any voltage drop across that fuse. No, there is. And Volkswagen came up with this about 12 years ago, and everyone said, you're full of beans, man. That ain't true. Well, now all OEs adopt this process. So we got 8.2 millivolt drop across the fuse. We have this chart. It's for the ATO fuse. There's the 8.2 millivolt drop. There's the 3 amp fuse that we have, because it changes for each amperage of fuse. And there it says if you have a 8.2 millivolt drop on a 3 amp ATO fuse, you're going to draw 264 milliamps. It works, guys. It really works.
Yeah, I'm just getting like a decimal 1 millivolt. I'm getting the same reading.
Well, again, it requires a very accurate millivolt meter. And the fluke meter that we have on this trainer will give you 1 decimal point. I would like 2, maybe 3. Let me just show you on my
I think that's what I think it's the meter is the problem.
I think you're right, but let me do that. Let me get rid of some of this stuff so I don't confuse you here. We'll just take a moment to do that. Okay, here's the ground. There's the positive. Let me go through the meter here. Alrighty. And then let me get, okay. Let me go to amps. Turn the switch on. All right. Okay, now I'm ready to share my screen. I'll just quick demonstrate this for you. Okay, see what I've done here. I've got my positive running through my ammeter up to the bulb grounded, and I get 270 milliamps. Now I'm going to take my favorite meter here, which gives me lots of accuracy. And I'm going to hook this to millivolts. And we'll see what the voltage drop across the fuse is. So we have 10.7 millivolts at 272 amps. So we go back to our chart, 272 milliamps. I'm sorry, what was the drop again? 10.6. So we go down to 10.6. I got to get to the second page here. I don't know if I have that or no. I didn't have the second page. But the second page would then show me about 270 some milliamps. It's very accurate. It's in the ballpark. It really works. Okay, so here's some more information on the charts and the procedure. Again, you need sharp probes to get right at that fuse terminal. All fuses that we have today have these test terminals on them. Okay, let's go finish up here. If you wish, you may want to consider buying a 1 ohm resistor. So let's just look at the current flow of this bulb. We've been dealing with this all day, so it's 264 milliamps. I'm going to ask you to predict what will happen if I put a 1 ohm resistor in series with a L1 194 light bulb. What'll happen? Anybody want to venture a guess?
1 ohm of resistance is not substantial, so it's probably not going to change it by very much.
Okay, I agree with you. Let's change my setup here so I can show you what I'm doing. All right, this goes to here. This comes out of here and goes to here. And now I want to go up to the bulb. Give me just a minute, I'll get this set up and then we'll demonstrate what we're doing here. Okay. So now let me show you. Will the current go up or down? Will the bulb be brighter or dimmer? And what is the voltage drop of L1 more or less? Someone said, well, we already know what the dynamic resistance of that bulb is, which is what, 50 some ohms? So 1 ohm shouldn't make a lot of difference. So here it is. The voltage drop is still going to be 14.5. The current's still going to be 264 milliamps. The voltage drop across the 1 ohm resistor will be 264 millivolts. Why? The dynamic resistance of L1 is 55 ohms. The extra 1 ohm resistor makes minuscule difference to the total circuit resistance and thus doesn't affect total current. Well, let's see if that's true. Here's my circuit setup. I'm drawing 271 milliamps. Here's my 1 ohm resistor. I'm going to put it in series with the bulb. I lost 2/1000th of an amp, but here's the trick. This is what's slick about this test. Hopefully you're going to like this because this has some serious applications on Ohm's law. I'm going to put a voltmeter and measure the voltage drop across that resistor, just like it says in the slide. And let's see what it says here. Now this meter only reads to 2 decimal points, so let me get my fluke meter out. That will give me more accuracy. There it is. $267.5 versus 268. So there's volts and there's current. So the voltage drop across a 1 ohm resistor in any circuit is going to be equal to the current flow. Now that has some pretty serious ramifications. What did I say? I said the voltage drop of a 1 ohm resistor connected in series to any circuit is going to be equal to the current flow in that circuit. Why? Let's prove it that Ohm's law doesn't lie. We have 14.5 volts, we have 55 ohms, and we have 0.264 amps. Current equals voltage divided by R, so we have 264. Voltage is 55 times 0.264 is 14. So that Ohm's law portion doesn't lie. Now let's change the value of the resistance to 1 ohm. Now we're looking at just the resistor. We have 264 milliamps of current. The voltage drop across the resistor has to be 264 millivolts because they only have 1 ohm. 1 times or 1 divided by is still going to be the number. Every time. Therefore, a 1 ohm resistor can be used as an accurate ammeter, but the wattage of the resistor must be high enough to handle the circuit current that you're measuring. So how many amps can a 100 watt 1 ohm resistor handle? Let's go to Mr. Ohm and find out. We have 100 watts divided by 14.5 volts is 6.89 amps. So that little resistor will handle easily 6 amps without causing any problem. If you want a higher current 1 ohm resistor, you get a 300 watt 1 ohm resistor. It handles about 20 amps. And here's how it's proven. So now we have power or watts divided by voltage, and we have our 6.89 amps. If we change that up to 300, that'll go up to about 20 amps. So an example of a higher current bulb. Here we have a 9004 bulb. Two different filaments, higher and lower, 5.07 amps and 4.41 amps. Now we can't do that on the trainer because the trainer only outputs 4 amps. So I used a battery here. Now I put that 1 ohm resistor in there. It dropped it to 4.10 amps, which means the bulb is dimmer than it was. If I put it on the dimmer side, I'd drop it from 4.41 down to 3.62. And if I measure the voltage drop across the resistor, it'll be very close to the amperage flowing in the circuit. Now, the more amps that flow, the little bit of difference there'll be between the volts and the amps, but not much. And the same thing is true there. So if we have that resistor put on the dimmer side, it dropped it to 3.55 amps. The voltage drop is 3.67 volts, which is very close to 3.55. This works every time. Now, think about this for a moment. Calculate the starting circuit resistance with a cranking amps of 250 and a voltage of 11.5. This is a very typical readings of a car that starts. Now, students don't think about dirty battery cables, corroded cables, loose cables. They just think my car doesn't start. Why? Well, what is the circuit resistance of a starting circuit? You're going to be amazed at this. If we use Ohm's law, we divide 11.5 volts by 250 amps, we get 0.046 ohms. That's almost zero resistance. But that's what a starter circuit has to have to get that many amps flowing through it. So what effect would a dirty battery cable or terminal have on that circuit? What if we put that 1 ohm resistor in series with a battery cable? Now we use Ohm's law, 11.5 volts divided by 1, which is our resistor, plus the 0.046, it reduced the current of the starter to 10.99 amps. Would that starter turn over? Absolutely not. You might not even hear a click from the solenoid. So 1 ohm resistance, which didn't make any difference at all to the 194 bulb, makes one heck of a difference on the starter. So the effect of a 1 ohm resistor is totally dependent upon the current flow in that circuit. So small resistance in a light bulb circuit, no problem. Put that same resistance in a starter circuit and the car doesn't start. That's the relationship between volts, amps, and ohms for Ohm's law. If you want to know where to get these, you can Google 100 watt 1 ohm resistor. You can get 5 of them for about $9. You need to convert the terminals to 4mm bananas. You just Google 4mm female bananas and you get some heat shrink tubing and you can make up that resistor. I got a whole bunch of them that I use for my classes. You can also use Mopar ballast resistors. If you don't have an ammeter handy but have a 1 ohm resistor, install the resistor in series with a circuit you are testing, either positive or ground, and measure the voltage drop across the resistor, which will be very close to the current flow. The variation slightly increases as the load current increases. So let me just stop for a moment and show you that. So here's my 1 ohm resistor. Now here's that 300 watt 1 ohm resistor. So let me simply unplug it and plug it in and see if the readings change. Same thing. It's just more wattage, but it's still a 1 ohm resistor. And I just converted it to the 4mm female bananas.
Yeah, so the 1 ohm is 1 ohm, doesn't matter. It's just
Doesn't
capable
matter.
of handling our flow for heat.
It's the wattage that determines how much current flows through it.
Yeah. Okay.
Just like you could get a 1 ohm wire wound resistor, but there may be 10 watts. You got to make sure that whatever current is going through that circuit will handle, the wattage of that resistor. Okay. We're going to give thanks to Mr. Ohm, Mr. Volta, Mr. Ampere, and Mr. Watt. I love those guys. They're all about the same age, in 1700s. We can provide you with additional training classes on the following topics: introduction to the oscilloscope, teaching oscilloscopes to your students, using scopes on the CL-1919-06, the EM330-1, the EM225, or I have a 3-hour class on the full buttonology of using the U-scope. If you're interested in those classes, get a hold of me. We'll be happy to do them for you, and the cost is free. I want to thank you for your time, guys. It's my belief that a successful electrical vehicle technician working today absolutely must have a solid understanding of Ohm's law, and more importantly, the relationship between amps, volts, and ohms. And with that, I will take questions or however you want to proceed. I do appreciate your time here. What do you think? Helpful or no?
Thank you. Very helpful.
Thank you. Very helpful.
You will get a copy of those 116 pages of all of the slides and all of the assignments and schematics that we covered. And you can make assignments out of it for your students, use it for reference, go to some of those links that I've given you on the web, and I think you'll find it helpful. If you want to go deeper into the Ohm's law, I have an advanced class on circuits that are not in the curriculum. We go into measuring the inductive kick of the relays. We see more about pulse width modulation. We measure switch bounce of the switches. I mean, we go real deep into it, but it's just a matter of what you guys want. Primarily, you're going to stick with basics of your students. I know understanding electricity is difficult because prior to the oscilloscope, you couldn't see electricity. All you could see were the results of it. The scope allows you to see electricity. In other words, a graphic representation of it. But whatever we can help you with, guys, if you never went to a vision class or a vision conference, think about it. It's always the first week in March. It's in Kansas City, Missouri. Last year, 3,700 people showed up, 3,700 technicians, auto instructors, and shop owners. The trade show is phenomenal. It's one of the best in the country. It's probably the largest in the country. But just stay involved, stay networking, and get yourself, sometimes you think, oh man, I only got 2 more years and I'm out of this place. I could not teach today if I were teaching. People ask me, you taught for 30 some years, 50 years overall. Would you teach today? I said, if I taught today, I'd be in jail in a week. Because I could not tolerate what you guys have to put up with every day. I have nothing but respect for you guys because it's not what it used to be 10 years ago, 20 years ago. I just, this acceptance of minimal performance and get a gold star and a trophy. No, that's not me. But I envy you guys. You guys do an awesome job. You got a lot of uphill battles. ASC Education Foundation says you got to do this, and this, and you say, yeah, I don't have time to do it. And now we're asking you to do more. Now EVs are coming. How do I adopt that into my program without killing myself? And I don't have any money. And I mean, I've been there and I've done that. I know exactly what you're up against. And you have my admiration. Any questions I can answer? General discussion. No? Well, guys, hopefully you have my contact information. If you want me to display it again, I will. But email me, text me, call, whatever you'd like to do. If you need some more assistance with anything or want to go over some of the details we covered today, I'd be happy to do that. This has been recorded. The recording is available to you. If you want, contact us. We'll give you the recording and the handout. The handout will automatically be sent to you via email, and I believe the certificate will also. But if you want a copy of the recording, I think we can provide that to you also. Anything else?
No, sir. Thank you for the information. Very good
Well,
class.
I
Thank
hope
you,
it
Dick.
was helpful, and guys, stay in touch. I'm here to help you, and let's work together. Thanks for your time, guys. I really appreciate it.
Great job. Thanks,
Thank you,
Dick.
Dick. Appreciate it.
You bet. See you now.
Thank you, Mr. Krieger.
Thank you.
You bet. Bye now.
Hey, Dick, thanks again. Really
Thanks, Dick.
appreciate it.
Oh, you bet. Anytime. Enjoy working with you guys.
You take care.
You bet. You too.